Temperature and kinetic theory. Thermal expansion. Thermal expansion occurs when heat is added to a substance. Say you have some sort of metal circular object and it's heated, heat is added. This object will expand in all directions, and so we can say the diameter of this object will increase. Now, looking at this object a little bit closer, it's still a solid object, and let's just look at a circle inside this solid object, and if we added heat, you can see how since the whole diameter of the object would increase, so would this circle that I dotted with red, that would increase. Now let's take a look at the circle. Let's say instead of having a solid circular object, we have a ring. And we heat the solid ring. What happens to the size of the circle inside? Well, since the whole object spreads out and increases in diameter, so does the circle on the inside without any substance on the inside, or we say the hollow part also expands. The gas laws and absolute temperature. So I want to start by talking with you about absolute temperature. Absolute temperature is used by a scale called Kelvin. Kelvin is a scale that shows that if you were to remove all of the heat from a particular system or substance, then that substance would have 0 Kelvin in temperature. That's equivalent to negative 273.15 degrees Celsius. This value of 0 Kelvin is also known as absolute zero. There are 3 gas laws I want to talk about. The first one is called Boyle's Law. And Boyle's Law says if the temperature is constant, then we can say that the volume within a particular material is inversely proportional to the absolute pressure. That's the same thing as saying the absolute pressure multiplied by the volume is equal to some constant value. Now, Charles' law says if the pressure of a substance is constant, then the volume is directly proportional to the temperature. In other words, we can say the volume is equal to some constant multiplied by the temperature. And lastly is the Gay-Lussac's law. If you have a constant volume of a substance, the absolute pressure is directly proportional to the temperature, or the pressure is equal to some constant multiplied by the temperature. The ideal gas law combines Boyle's law, Charles' law, and Gay-Lussac's law. And with that, we can see that absolute pressure multiplied by the volume is directly proportional to the temperature, or the absolute pressure times the volume is equal to a constant multiplied by the temperature. It turns out this constant value is equal to N, which is the number of moles of your ideal gas, multiplied by another constant of R. So N is your number of moles, and R is a value of 8.314 joules per mole per Kelvin. This may be a slightly different number than you're used to using in chemistry because the units of our constant are different. Now, when we combine the constant with the above equation, we get PV is equal to NR T. We can also write this equation as PV is equal to capital N KT. Now the capital N refers to number of molecules instead of number of moles, and the lowercase k stands for the Boltzmann constant, which is equal to 1.38 times 10 to the minus 23 joules per Kelvin. Now, I wanted to show you an example of how to convert volume to moles, then to number of molecules, using standard temperature and pressure, or STP. So, say you had you breathed in a volume of air, 1.0 liters of air, and what I wanted you to do is to determine how many molecules are there in that 1 liter breath of air. So how many molecules, or find the capital N value here that we would then plug into the formula above of the PV equals NKT. So if we had, again, a volume of 1 liter of air, how many molecules are in there, and that value would go in for the capital N. So we're solving for capital N. So we know that using standard temperature and pressure, that 1 mole of air, the volume of 1 mole of air, has a value of 22.4 liters. So 22.4 liters of air is equivalent to 1 mole of air. Now if we breathe in 1 liter of air, how many moles of air are we breathing in? So I will write this as, for every 1 mole of air that has a volume of 22.4 liters, I'm going to multiply that by 1 liter that I take in a breath, and the liters will cancel, and I am left with 0.045 moles of air. Now what I want to do is to convert this value of moles to molecules. So I'm going to take my 0.045 moles of air, put that over 1, and I'm going to convert moles to molecules. And I know that for every 1 mole of molecules, that's equivalent to Avogadro's number, which is 6.02 times 10 to the 23 molecules. And so by multiplying those two values, the moles, the unit of moles, of course, cancels. I am left with approximately 3 times 10 to the 22 molecules. So my capital N value, which I'm solving for so I can plug it in my ideal gas law equation, my N is approximately 3 times 10 to the 22 molecules. So put a little red box around that. Now lastly, I want to talk with you about something called kinetic theory. And this is the kinetic theory of ideal gases. And that is your average kinetic energy of the ideal gases is directly proportional to the temperature. So the motion of your substance at the molecular level is directly proportional to your temperature. So if you double the temperature of a substance, you have doubled the kinetic energy, and therefore, or the average kinetic energy of the substance. Now we know average kinetic energy is equal to 1/2 m, and this is the average velocity squared, and that's directly proportional to temperature. We can also write that as 1/2 m average, or the mean speed, whoops, here, not subscript, but squared, is equal to some constant multiplied by the temperature. This constant ends up being 3 halves k, where k is the Boltzmann constant. So putting this formula together, we have 1/2 m, the mean speed squared, is equal to 3 halves kt. This is our kinetic theory of temperature. Now, what if we wanted to solve for this speed? Solving for this speed would give us something called the root mean square of the speed, or the VRMS. Root mean square just means take the square root of the squared mean value of the speed. So that would be the square root of the mean squared. Now, if we solved for that, that would be, using the above equation, that would be the square root of 3kt over m. So that is the root mean square of the speed of your molecules of your ideal gas. Okay, here's your practice. Good luck.